Hi there, and a really warm welcome to this week's Quick Tip. I know I've been calling them Quick Tips while they are 20-minute plus videos, but let's call it tradition by now and let's just keep going with it. Now, this week we are having another special one, something I discovered also along the lines of my Opal research, and this is a shading normal respecting Falloff shader. And we're not only going to take a look at the shader done with nodes, but also by a OSL script, and this will be the first time we are doing OSL in my tutorials. So let's buckle up, get some coffee, and let's keep going. Welcome to 3D Land. Let's see what we are going to do today. So on our agenda today is making a Falloff shader. So the usual Falloff shader is like this. So we get a gradient from the direct viewing position, so where we look at directly on the sphere, to the rim of the sphere, and therefore we get a gradient from one to the other. Now, the shader we are going to do is completely the same. So this is the shader we are going to do today in terms of nodes. So if we plug that in, it is completely the same here. And then we are going to do the same again using a script with the open shading language. Here we go, also the same. Now I see question marks shooting out of your head, and this is rightly so, until I introduce the last thing in our row here, which is a normal map. So if we introduce the normal map into the normal here, you get this weaving pattern again. You might be familiar with it from the last tutorial about cloth, link in the upper right corner if you're interested. So now let's do the same thing again. So we are going to our Falloff map, and to not make it too boring, I also choose a gradient so you can see all the angles that are represented here, and you can see what's at miss here. And this is that the normal map and the normal orientation of the map is ignored by the Falloff. It's just following the surface of the object and the smooth surface that is. So this is where the difference comes in with our maps. So if we choose our maps, those respect the normal map. So when we just lessen the strength, you can see it very easily and nicely. Those are respecting the shading normals. Also, our OSL script is doing the same, obviously. So instead of having like those couple of nodes hanging around in your node tree every time you want to do that, you can do that more easily with just the Falloff shader in the open shading language. This has the potential to be a very short tutorial and give the association back to quick in the quick tips, but I'm not sure about this because I tend to stuff tutorials full of information, so let's see how this is going. Okay, as always, let's start from scratch by creating a new material. You can go in here to Octane materials and create a diffuse material, call it Falloff, and then assign that material here, and then care about the information we need to get the Falloff shader going. Essentially, we need two different sets of informations. One set is the direction we are looking at the object, and the other set of information is the orientation of the faces of the object. Luckily, Octane has nodes for both, so what we need to do to get the ray direction is just type that in, so ray direction, and you can see there's a shader for that. Here we go. And then we need the set of data that gives us our surface orientation of the object. And this is usually called normals. So let's try and search for normals. Here we go. So we already have both sets that we need handy here. Now there's a couple of things we need to set here. So for example, in the ray direction, we are going to set the view direction to off, because this is something we need to care about, the orientation of the ray. This is giving us the ray from the object to the camera instead of from the camera to the object. So let's tick it off here. Now we have to find a way to combine both of those sets to give us our Falloff. And this is usually the dot product. If you want, you can follow me into the next chapter, which is a chart time again. Welcome to Cinema 4D Chart Time. Let's actually explore what I just said in a more broken down schematic view here. So we have a camera, and in the field of view of the camera we are shooting rays towards the object. And then the object has normals that point along the surface orientation of the polygons. And we have a dot product, and the dot product compares those both angles. Now for the dot product to work, we need to invert our camera rays so they go from the object to the camera in that kind of manner. And then we can compare the angle between the camera ray and the normal ray. And this gives us the color that we want for our falloff. Small interlude here. Normally we have to cap the vector to a unit vector, so it's exactly 1 unit long in order for the dot product and later the falloff to work. But Octane does that for us, so we don't have to do anything. With this slide, let's inspect the dot product a little bit more up close. So we have a dot product slider that is sitting at 0. So when we just move our vectors, you can see the dot product moves. So when both of those vectors are at the exact same position, the dot product should be 1. And when they are 90-degree offset, then it's 0. And this goes for both angles. So when I move those angles, you can see it's always the comparison between both of them that leads to a 1 or a 0. So when I move this one vector to the exact same position as the other, the dot product is 1. And when I then rotate it away slowly, then it becomes 0. And this is exactly what we are searching for and what will give us our gradient. Now that we know what a dot product does, let's go for one. So let's hit tab and search for dot product. There's nothing popping up, but you know that a dot product is math and we need 2 inputs. So let's go for math, and then we need binary inputs, so 2 of them. Here we go. And if we search around, we can find the dot product somewhere. Here we go. And let's make this a little bit bigger, and then pipe both of those information vectors in here. And then let's see what we've done here. Alright, this is looking like a falloff, but it's very faceted right now. This clearly has something to do with the polygons. So if I expose the mesh here and go to wireframe, you can see this is exactly the same pattern. And this comes from the normal here. And when we look closely, the normal type is set to geometric. That means it represents the unsmooth geometric normals. Now, we don't want that, obviously. And this is where we also get to the nice shading that comes from the normal maps. So when we roll that down, you can see we have multiple options. So the falloff Octane uses is the smooth falloff. That makes the falloff smooth, as the name suggests, but it doesn't respect the shading normals. But we want that, so we are going one step further and setting this to the shading normals. So now we can load in normals and get the right representation of the falloff. While we could easily end this tutorial right here and honoring the name of the quick tip, this is not quite what I have in mind. There is also the OSL part at the end. But beside that, I want to linearize the shader. So for now, this shader isn't linearized. What do I mean by that? This is best seen if I invert the shader here by a invert node. So let's pipe that in here. And you can see now it's fading from black to white. And let's also call a falloff. Here we go. And let's compare those. So let's set the falloff to 1. This makes it linear. And when we pipe in the falloff map, you can see the black dot is much smaller than with the shader we just did. And this is a factor that comes into play if you want to gain linear shaders, which are important if you're doing mathematically or scientifically accurate shading. So why is the dot product not linear? Nice that you asked. Let's go back to our chart time to explain that. Welcome back to chart time. So what I did here is to animate one of the vectors linearly, so the speed of the vector itself in which it rotates doesn't change. But if you look at the value the dot product gives us, you can see that it begins slowly and then it increases speed ever since. And this is what gives us the non-linear response for the dot product. But fear not, there is also math that can help us here, and this is the Arc Cosine. Alright, let me explain to you what we just established in a little bit of another way, so you get it ingrained in your brains. So we are looking at the center of our sphere, and then we let our view wander to the rim of it in a linear manner. So we have a constant speed in which we are wandering to the side. And what we are interested in is the slope of the sphere at the point we are looking at it. So when we are starting the first few units, the slope doesn't change that much, but the last couple of units, there is a rapid decline in slope. And this is what the dot product gives us, and this is also the non-linear way. So what the arc sine or arc cosine is doing is giving us back angles, which is a much more predictable way to get the right values out of there. Because a 45-degree angle is exactly the middle between a 0-degree and a 90-degree angle. So let's do this. Let's actually go about that. And we need a math unary for that. So math unary. So we only need one input. And what we are searching here is the arc cosine. Here we go. Now we don't need the invert anymore. So we are almost there. But if we compare, you can see the falloff here is going to the rim and gives us the white value exactly at the 90-degree angle. While what we have here is the white value a bit further into the sphere. And this is because the arc cosine gives us radians values. And it gives us the radians value of a 90-degree angle. And this we need to figure out and then compensate for that. There's of course multiple ways to get to this value, and I used Google. So what I did is get 90-degree in radians in there, and this already gives us the result. And this is the formula if you're interested. So let's copy this value and head back to Cinema 4D here. And what we need to do now is to divide what's coming out of here by this set radians value. So let's do so. We need another math binary. So let's copy that and put it in here. And we need to set this to divide. So instead of dot product, let's set it to divide. And then we need something to hold our data, which is a float texture. So let's paste our data in here and then divide our outcoming data with the radians number here. So let's see what this is doing by comparing it to the falloff. And yes, now our shader is working. We have made a linear shader that should now, let's get our normal map from here, work with normals. So when we are pasting that in here and adding it while the falloff map is still active, you can see the falloff map doesn't care. And when we are going with our shader, you can see now our shader is respecting the normals, as we set the normals to the shading normals. If we want to have the same result as the falloff, we just have to set this to smooth, and then we get the same exact result here. Okay, let's clean this up real quick. And also name it. Here we go, so you know what you did here, and the naming of the nodes reflect that. Next, let's have a look at the OSL version, which should be very easy to do. So it's a good entry for you and me, both starting coding with tutorials and you learning. So let's get going. Small interlude once more. So while editing this video, I thought maybe it's a good idea to explain this whole Radians thing in a chart time. So let's do so. So what we are looking at with an Octane gradient is a 0 to 1 range, and the middle gray is exactly 45 degrees. So we can measure in degrees and therefore have a linear curve to build up on. And what the dot product is giving us is not a linear curve. So the 45-degree angle is 0.8 or 0.75 instead of 0.5, the middle gray value. So what we need to do is get an arc cosine going that measures the dot product and gives us back angle values. But what the arc cosine also is doing is, of course, stretching out the values, because this gives us from 0 to 90 degree, or what 3D programs use, radians, from 0 to 1.57 radians, which equals 90 degrees. What it's of course also doing is spreading out the degrees in a linear fashion. So when we then put it down back to our original size from 0 to 1, we have the middle gray value representing 45 degree. And we do that by dividing the output value by the 1.57 degree radians. So we get a value from 0 to 1. And therefore we have recreated the linear falloff that also Octane is giving us from the start. Okay, on with the OSL scripting now. Alright, so to not get confused with anything in here, let's actually create a new material by going to Materials and another diffuse and call it OSL. And also, of course, applied to the sphere. So here we go. Let's first of all paste our normals in here so we have them. And next, let's call for an OSL script. To do that, it's very easy. Hit Tab and then OSL. And just choose the first that pops up, which is a add OSL. And then when we are linking that to our diffuse and we are activating that, what you can see is the code here. And this is already a good indicator what we are doing. Now, I don't recommend you to script in here. Let's open the editor. Always script in the editor because this is a better experience than just the window that pops up in the node tree. Since this is code, we have to establish that it's working. So we can compile it, and if the compilation is okay, that means the system doesn't have anything against it, and it will run mostly error-free. So let's go and have a look at our script here. So we have different inputs, and the inputs are declared here. So we have color A and color B. This is what the input is all about. So if I would change this to vector, it would input a vector. And if I change this to float, it would have a float input. So usually within Octane, you input colors. And then it has one output. Usually OSL allows for multiple outputs, but this is a limitation of Octane. It only can have one output. So we have output color C. So output goes color to color again. And then we have something where we can do our math. And this is in between. So we say the color output is the input A plus the input B. And this is very easy to understand. So let's go about and create our own shader here. Our shader doesn't need any inputs, so let's just delete both of those. This will lead to an error if we want to compile now, because the inputs that are mixed here are not there anymore, so they are not declared. So let's also delete them from here. So what we want to do is get in the both shaders. So if you remember, we have the camera ray and we have the normals that we need to pull in here. Fortunately, this is a very easy thing to do because in scripting languages there are so-called global variables that can be just loaded in so the shader or the script knows what to do with them. And we are going to do that right now. So what I need to do here is go ahead and then call a float. So we want to work with float values and then call that a name. So we are basically setting up a variable. So we are writing something in a float value that we declare with a certain name. So let's call this Falloff. So this float is now called Falloff. Now we have to describe what this float is made of. So we go with an equal sign. And now we need to do our dot product inside of there. Dot product is just dot. And if you're wondering where I found all the information about this, there is the OSL Script PDF, which became my Bible more or less. So let's have an example right now, because I want to have the camera array and also the normal. So I don't know what those are described as. So when I want to get the information, let's open up the PDF right now. And if you are at the right position, of course, you can find it here. You can see that there are variables for all of those things. So for example, we're searching for normals, and the variable for normal is just a big N, while the vector I is the ray that we are searching as our camera ray. So we already know that we need I and N. And this is what I'm talking about. I'm just going through the PDF and learning stuff about the scripting language and what types of argument and variables you can use. So let's return to our Cinema4D file here. So we now have to declare the dot product, and usually the distinction is a comma. So we have to find the I and the N. What we also could do is just write in the N in the output and see if that gives off anything. So compilation is okay. And when we render now, you can see, yes, it looks very distorted. And this is because the vectors usually go from 1 to -1, and Octane can't deal with minus values in the shading real nicely, so it looks a bit distorted. But we're getting some information out there. Let's try the same thing with the I. Here we go. Compile, wiggle around a little bit, and, well, something's happening, but it's rather black. And we also established that we have to invert our ray. So what we need to do actually is -I, because we want to have the ray from the object to the camera and not from the camera to the object. So let's try this. Wiggle around a bit. Yes, so we inverted our rays here. We need to do that for our dot product. And to see what we just did, we just copy the Falloff name and paste it here and compile. And now we are ending up with our first Falloff shader that we had before we used our linearization, before we used our Arc Cosine. We could write all of that in the formula back here, but let's split that out into more sections to be more easy on the eyes and phrasable when you're looking through that. So add another line here, and what we want to do is another float, and let's call that linear falloff. So lin fall, here we go, then equal sign, and what we need to do now is the arc cosine. Fortunately, there's also a function for that. A cos is the arc cosine, and then what we need to do is bring in the falloff in here. Let's do this. Here we go, and bring in the falloff. Don't forget the semicolon here, otherwise it won't compile. Here we go. Let's see what we've done here. Okay, so something went wrong. Oh yeah, we are still using the falloff. We want to use the linear falloff here, of course. So now we have our linear falloff, and the only thing that's missing is our arc cosine that we need of 90 degrees. Now there's a neat trick here, because we can compute our arc cosine right in the script. So what we can do here is go with another float, so float, and then we are just calling it rad for radians, and then equals again. Now there's a function where you can convert radians to degrees and otherwise the other way around. So we are calling the radians function, and then we are just typing in 90 degree in parentheses after that. So we are wanting the radians number for a 90 degree angle. And we can get this now, so you have to trust me on that one. Now what we want to do is divide all of that by this value, as we did in our notes. So what we could do is just go with more parentheses here, and then we divide that by this name, rad, which carries the value of a 90 degree radians. So here we go. And then, of course, we already have that as our output. So compiling that, so we now have made a mistake somewhere. So let's see what this is all about. Yep, small spelling mistake, so it's Radians. And that should fix it. All right, compilation okay. And now if we wiggle it around, we have our perfect Falloff shader. And now, last but not least, let's see if it works with our normal map. So let's give that in our normal. And yes, our shader works. So this is how you do a OSL shader on the quick way. Of course, this is not all that OSL can do. It can do a lot more, but this is a nice entry into that coding level of OSL, I think at least. So last thing to do is call our shader the right name. And we could also call it normal respecting falloff or something. But this doesn't show up anywhere else than in the shader. So if we want to get our OSL script in the right manner, we need to go to basic and then just type falloff here. And by this, you have another tool under your belt as a shading artist that gives you very, very nice results. And it respects bump maps, normal maps, and all the surface variations you do with your object. So in essence, it's giving you a much more realistic output for your falloff than the built-in Octane falloff. For example, if you're doing a nice iridescent shader and use normal maps, this of course gives you a much more lifelike result than with the falloff that comes packaged within Octane. If some developers are hearing this, please build in this functionality within the shader so we don't have to do those complicated things to get better shading and better materials. I haven't edited this yet, but I think we are well over 20 minutes again. Hopefully you liked what you saw, you stayed nerdy and curious, so thank you very much for watching. Also a huge thank you for my Patreons who are supporting me and making content such like this possible. I am very happy to say we are nearing our first goal, which is 1,000 euros. This is immensely appreciated, especially through those 50 euro tier subscribers, Shields Augustinen and Leon Studio TV. Thank you both so much. But also through the great help of my 15 euro tier subscribers, AB Studio, Anton, Pavana, BVR, Computer Generated, Eduardo Vigetti, Etienne Schmidt, George Luna, Harish Pavaskar, Jacob Fung, Joy Ciccoline, Just a Frickin', Chris Clemson, Ludger, Lucas Pazon, Marty Kane, Part 1 of 2, Raiko, Render King aka Alessandro Bonchio, Scene CGI, Shamus Johnson, Terry Wayne Ranson, Yassin Rupp, and Shibue Chang. Also a massive thanks for my 5 euro and 1 euro tier subscribers. I'm really thankful for all of the support I can get. My dream is to make a living out of that, and every day you bring me closer to that goal, and I'm massively thankful. And this concludes this week's quick tip. If you're still watching, I thank you very much for your loyalty. Show it to me by posting a ball or dot, for dot product obviously, in the comments down below. Thank you very much. And with that I say a great week, an amazing time, and happy coding. Bye.